We live in exciting times, don't we? What has happened recently in recent years in AI is just opened up the scope amazingly for humanity. I mean, when I think about it, and I'm thinking into the future, I just lead ahead as much as my imagination would limit me to. So it's just amazing. What has happened recently is models that used to be tens of millions of parameters have become hundreds of billions of parameters. That's 4 orders of magnitude larger models. It has completely opened up the space on the possibilities of what AI can do. It has also created problems. When you have such large models that you have to run through, you need a lot of compute. And to get a lot of compute, you need a lot of power. So whereas mass deployment of AI has just opened up a whole bunch of possibilities for humanity, they has also created challenges for us to handle. If you look at where we were and where we are going, the main problem was training these large models. That issue has now moved from training to mass deployment of these models. We have now trained these models, and to really use them in different use cases and really help humanity, you have to deploy them across billions of people. That is inference. If you look at where we are going, in the near future, 80% of all your compute requirements is going to come from inference, not from training. But what is the problem it causes for us? If we only just look at the very near future, 2027, the power consumption to service this is expected to go up by 160%. And I'm not even talking much further down the line. I'm just talking 2 years ahead. 40% of our data centers are expected to be starved for power. And we have to solve this problem. If we really look deeper down, where is this problem coming from? This power efficiency problem is essentially coming from our GPUs and the compute ecosystem around it. 70 to 90% of the power consumed in a data center comes from computation and memory access. Of that, 40 to 60% is computation from GPUs and accelerators. And when I say computation from GPUs and accelerators, I also mean on-chip memory access, because it's all about data movement from your on-chip memory to your compute elements and data flow. That's where most of the power consumption is going. To add to that, you have a much bigger requirement for off-chip memory access, which is even worse, which is 20 to 30%. You combine the two, you have 70 to 90% of your power being consumed by your compute platform. The remaining 10 to 20% in the data center comes from other components, networking, cooling infrastructure, what have you, storage. So if we need to solve this problem, we need to solve the power efficiency barrier that we have. Now, interestingly, when you see this picture, it reminded me of Sisyphus in Greek mythology. Sisyphus was a very cunning and devious king, and he deceived the gods. As the story goes, when he died, Zeus was very angry with him, so he condemns him to the underworld. And Hades, as a punishment to Sisyphus, makes him push a boulder up the hill. As soon as he gets the boulder up the hill, it rolls back down the other side. So for eternity, he is condemned to roll the boulder up the hill. And that is the kind of problem that I find us in. With just increment innovations in GPU and accelerator architectures, we are constantly in this race of trying to get higher performance, but being limited by power consumption and by the economic viability of trying to do more and more with AI. Well, how does that work? You want to do more with AI, you need higher compute. The more compute you need, the more power you consume. The more power you consume, the more you have to do to manage that power, not just distribution and delivery of that power, but also heat management. And you have to scale technology. The more you have to scale technology to manage power, your cost is going up. The higher your cost is going up, puts a damper on all the applications you could possibly run using the neat new technologies we are developing. So this is really a constraint across the board. Hyperscalers are spending hundreds of billions of dollars on infrastructure build out, and they are starving for economic viability, which is intimately tied to power efficiency in the data center. If you look at what the economic model in a data center looks like, 88% of your CapEx comes from your compute platforms, your GPUs and the associated HBM memories and such on it. That actually translates to 62% of your total cost of operations at the data center. That's huge. And you add to that all the power consumption that goes, which is the OpEx cost, totally amounts to 72% of your total cost of operations at the data center is just coming from your compute platforms. So we need to solve this. To solve this, we have to rethink the problem from ground up. We really should look at the problem and look at what is it that we are trying to do. What are the use cases we are trying to implement? What are the kind of workloads? What are the kind of models that apply to those workloads? And how to most efficiently build the technology that maps to those models. And we eventually, once we know what technologies will map to this problem paradigm that we have, we need to align that so that we can meet the unmet needs of compute and power and economic viability in the data center. How do we go about it? Let's just take a quick look at the stack. Where is all this happening? You have power generation and distribution. There's a lot of innovation that can happen there. I was amazed to see there are these small modular nuclear reactors providing about 500 megawatts of power that are now being attached to data centers. So there's a lot of innovation there. There's a lot of innovation that can happen on heat management. Data centers are being built which are submerged data centers. Maybe we need to build a few in the poles, the kind of heat that is being generated. But there's a lot of innovation that can happen there. Fundamental to all of this is the hardware, which is we were talking about. That is what is requiring the compute. That is what is costing us a lot. That's what's creating all the power and the heat that needs to now be managed. There's a lot of innovation that can happen there in terms of architectures and such. Connectivity is data movement. When you have mass adoption, there's a lot of data that needs to move. And how do you innovate on the connectivity side with optical innovations and such, across the board? The last but not the least is software. And I want to talk a little bit about it because it transcends across the stack. What you can do with software today is if you want to save power, if you want to save compute for inference, there's a lot of what you can do with software in terms of numerics. Used to be 32-bit floating point. That's where we started. Went to 16. Went to 8 floating point. Went to block float 8. Went to int 8. Int 4. Every time you go from 32 to 16 to 8, you reduce your power consumption by half. So these are just training algorithms and quantization algorithms that can happen and that can really help you down the line in terms of how much power you consume. Software. You have a node of GPUs. The software can be designed to figure out where you take your use cases and how you shard the use cases or the users across the compute available to you. So there are efficiencies. There are companies working on that, trying to make it most efficient in how you manage your workload across GPUs. Software. You can take one GPU and break it down into virtual GPUs, multiple virtual GPUs. Shard your workload across that. software and hardware, you can position your workload in such a manner, shard your models in such a manner, that you reduce the amount of bandwidth required for connectivity. That unclogs your bandwidth requirements at the backplane, and it also just opens up more performance from the same platforms. But fundamental to all of this, what is the heart of it all? The heart of it all is the hardware, is the compute core. What is the blood that the heart is pumping, the data that you're working on? And that is fundamentally, that is where your bottleneck is. If you look at the entire stack, you solve that and you solve everything. Everything is built around it to solve that. Yeah? So, what do we do here in Sagence, right? We take the 40 to 60% of the power in the data center that's being consumed by the compute. And by the way, fundamental to that, there are techniques that are trying to reduce it, but effectively, like the in-memory compute techniques, which are digital, but digital techniques are mostly near memory compute. They get you somewhere there, but not all the way there. But you still have to read the data from your SRAM and move it to the digital in-memory compute elements because the adders are still there. What we do here in Sagence, we reduce the power consumption in the compute node, 10x, and I'll talk about how that is. We reduce the power consumption with the off-chip memory access by an order of magnitude as well. And we don't do anything to the other components. But together, with these two elements, if you can reduce the power consumption by an order of magnitude, you are in a very sweet spot. You solve a lot of problems for the industry. Of course, the question, right? The question comes on how do we do that? And really, the final frontier of being able to do that, however many challenges there are, the final frontier to be able to do that is not that you move on your chip, that you move your storage closer and closer to compute, or even interleave it while keeping all the adders and the multiplexers in place. The final frontier is to collapse the two. So what do we do? How do we achieve it? What we do is, in one transistor, we use multi-level technology. So we have a 24 to 48 to 1 advantage in storage density because we're using multi-level. We don't need 24 to 48 transistors to store a parameter. Just one transistor. We use the same transistor to do compute. We don't need a 500 transistor multiplier to do compute. So we have a 500 to 1 compute density advantage. And there's no data movement between compute and storage. See, I was talking all about this time that all the in-memory compute, I was going to talk about this as what needs to be the solution to this problem, at least in the near future, is just collapsing compute and storage absolutely to one unit, trying to reduce that unit in size as much as possible so that you get good economic viability, right? So that's what we at Sagence do. But other companies are looking at this too. They are looking at some digital solutions which get you someplace there. We are trying to go to the promised land, right, with all the bells and whistles that's needed. Now, with that, what it gives us now, if we can solve the power problem, we inherently solve the cost problem too, because we don't need to scale technology to reduce power consumption. We can get very high performance without having to scale technology. So now that opens up the whole landscape of what is possible in terms of content generation applications that are possible, in terms of robotics, because robotics, I see that as a huge, big, my vision is there'll be robots all over helping us out everywhere, but they will be all power constrained, battery operated. So power is a huge consideration there. And then the whole range of applications, in manufacturing, defect detection, and so on and so forth, right? All of these open up because now you've solved the heart problem and the blood movement problem. In conclusion, I'd say that economic viability of generative AI is inherently tied to power efficiency barrier that it presents. And new silicon architectures are absolutely necessary to solve the crux of the problem. And of that, what I see clearly is that much like our brain cells, we need to integrate both the storage element and the compute element into one unit. And that, I think, gets us to the point where we are now solving the very fundamental problem at the leaf level, not at the branch level, not at the trunk level, at the leaf level of what we need to do to really enable mass adoption for inference.